Alrighty, let's see what we got today. It's easy. Special positions in a binary matrix. Given an n by n binary matrix mat, turn the number of special positions in mat. Position ij is called special if mij equals 1 and all other elements in the row I and j are 0. I see. So 1 here. So only this one is the singular 1 in its row and column. All these are ones. Does it return the number of special? Yeah, number of special positions. Okay. Obviously you don't want to just go through the ones and then iterate all the cells in its row and column. I think in order for it to be special, the element has to be, so I think if I kept track of the count of the number of elements in a row and the count of the number of elements in a column, and for every position that's a 1, if the count of the number of elements in that row and the count of the number of elements in that column is 1, then it has to be special. So I need to have the counts first before I iterate over the specials. Let's see. It's a 100 by 100 matrix, so there's up to 10,000. Up to 10,000. I'm wondering if I just do 2 passes over the elements in the matrix. If I don't do 2 passes, the first pass to do the counts, and then the second pass to check if the cell is a 1, and if it's a 1, then check the counts in its row and column. If I don't do that second pass, I can store the positions of where the 1s are in the first pass and just iterate over those positions. It could be up to 10,000 positions. Alternatively, for each row, have positions of where elements in that, for each row, have the positions where there's a 1 in the column, and for each column have the positions where there's a 1 in the row. And then I can skip any columns or rows that have multiple in them. Okay, so instead of doing counts, I just store lists of, okay, so for each row, store list of column indices with 1. Okay, so row 1's, so it would be something like so let's go ahead and define the rows and columns as the actual constants. So the number of rows is the length of the matrix, the first kind of dimension, and the number of columns is the length of the first row of the matrix. And so for every rows, I could initialize it here. That's fine. So for every row, or R in range rows, let's say column 1's actually is the name of that one. So current is going to be an empty list for every column. I guess I can just do a for each loop. So for every element in this row, so for every element element in matrix at this row index, if no, I need the index. I'm pretty sure I need the index. Yeah, I'm pretty sure I need the index. Yeah, okay, so for column and range calls, if matrix at this, well, I guess I'll just do C, at this row index and column index is equal to 1, then call 1 is going to append this column index. And then after this, I need to do, current appends this. Current stores the stuff for this particular row, and then calls 1's appends this current row. And then for each column, store list of row indices with 1. Do I? I will. Yeah, this is bad. Or this is. I should just initialize empty list for both 2D arrays. Okay, so I'll do call ones is going to be a list for each in range the number of rows, and then row ones is a list for each in range calls. Okay. Similarly, for each column, store list of row indices with 1. So this should just be iterate over every row and column. If there's a 1 at this position, then call 1's for this row is going to append this column. And then row 1's for this column is going to append this row. And now I need to iterate over the 1's maybe. No, I think I can just choose to iterate over one of those two. So let's say for every row in call ones, so this is the list of where the column indices with 1 for this row. So I'm going to skip it if there's multiple, if the length. If the length of this row is more than 1, is not equal to 1, then skip it. If it's 0, then there's just nothing there. If there's more than 1, then they are definitely not going to be unique, or not going to be special because they're sharing the same row. And then I guess I can just say the single column is row at 0, and then I'll check if this is if if the length of row 1's at this column is equal to 1, then this is special. I think that might be correct. Okay. Question is whether or not this might be fast enough. Okay, it's decent. So what would be maybe better than this? Create my list for each row and column. Iterate over every element. Store in the appropriate list. This doesn't look that easy of a solution. I guess there was maybe a more brute force way that was relatively easy to understand. For every row and columns. Yeah. This is pretty efficient in terms of just skipping over stuff that doesn't apply. It also kind of stores the locations. I see. I think it's possible for me to just store a counter for one of the dimensions, or one of the 2D arrays, and then, or like, I store the actual column indices for the rows, but then I just store a counter for the other way. That might be slightly better. It's kind of weird to do. It's kind of weird to do, but row counts. So this would be for each column store count of rows, count of basically ones in that column, same as the number of rows with ones in that column. So it would be just row counts would be 0 for everything in range. I guess I can just do multiplication. 0 times the number of columns. So here there's many row counts of this column index is going to add 1. And here this would be if row counts at this column is equal to 1, then answer increments. Okay, so not list, but kind of the same. Okay, I guess that was good enough. Interesting. I don't think I could have gone to this kind of this optimization without having to do kind of a slower but more easily understandable symmetric idea of rows and column counting using lists for those indices. Okay. All right. A summary. Um, Also, this could just been random. Could have been equally as good as the other one, but just need to run it another time. Summary. Keep track of the kind of, okay, so for each row, keep track of the column indices of where there are ones in that row. So I use a 2D array. Yeah. Well, I don't know why I use, I would say use a 2D array where kind of, yeah, where row index, is it row index? Yeah, where row index corresponds to a list of columns. Yep, and then also for each column, keep track of the number, number count of row indices where there are ones in that column. Use to fill out both. Use a single nested for loop, iterating over row column indices in the outer and inner loop. That adds to the list or the count when of those arrays, I guess, 2D and 1D array. When the element or when the value at that row column is 1. Lastly, iterate over the 2D kind of 2D array for rows, the one that is tracking the column indices, ignoring when the row has multiple column indices, since they would prevent each other. So if a certain row has, let's say, column 2 and column 5 as ones in it, then those two spots would prevent each other from being special, because the 2 and the 5 are on the same row, right? Prevent them from being special. If a row has one column index and that column index and that column has one row count, so if the column only has one in it, and there's no other rows that have 1 in that column, then it must be special. Track using answer. Track count of answer. All right, time complexity. This is going to be O of n squared, O of mn, where matrix is n by n. Since you need to iterate over every element of the initial matrix to determine the arrays later on. The arrays to say which column indices have ones and which the count of the rows. Yeah, space complexity, this can be O of mn, since in theory all values in the array could be 1, in the matrix could be 1, such that the 2D array of column indices that have 1 have the same size as the matrix itself, which is obviously n by n. Alright, cool beans.